Hi students, in this video we are going to talk more about tangents and normal to the parabola, then we will be solving problems. Next theorem, the equation of the chord joining the points x1, y1 and x2, y2 on the parabola s equal to 0 is s1 plus s2 equal to s12. This theorem we are going to prove for only standard equation of the parabola, but theorem is true for general equation of the parabola. Here s equal to 0 could be representing general equation of the parabola. Okay. Also, this s1 plus s2 equal to s12 is a line equation, not just line segment. So we should rather say equation of the secant joining the points x1, y1, x2, y2 on the parabola s equal to 0 is s1 plus s2 equal to s12. Okay, fine. The proof that we are going to give here is kind of a verification proof. What we do is, first we will show that this s1 plus s2 equal to s12 is in fact a line equation by showing that it is a first degree equation x and y. Then we will show that this line equation will satisfy these two given points x1, y1 and x2, y2 on this parabola. So that's why this s1 plus s2 equal to s12 must be a chord equation, or you should rather say secant equation joining the points x1, y1 and x2, y2 on this parabola y square equal to 4ax. Okay, fine. Let x1, y1 and x2, y2 be 2 points on the parabola s equal to 0. Here the parabola that we consider is standard equation of the parabola y square minus 4ax equal to 0. Since x1, y1 is a point on the parabola s equal to 0, we should have y1 square minus 4ax1 equal to 0. That means s11 should be 0. Since x2, y2 also point on the parabola, we should also have y2 square minus 4ax2 equal to 0. That is s2 to 0. Fine. Okay. Now let us consider the first degree equation, that is s1 plus s2 equal to s12. What is s1 here? According to our notation, s1 is y1 minus 2a of x plus x1. s2 is y2 minus 2a of x plus x2, and s12 is y1 y2 minus 2a of x1 plus x2. Okay, if you simplify the whole thing, you will end up with the first degree equation, that is 4ax minus y1 plus y2 of y plus y1 y2 equal to 0. Feel free to verify this. As you can see, this is a first degree equation in x and y, so it represents line. Fine. So this one represents a line. Okay. Now we are going to show that this line will satisfy both the points. Okay. Now simply substituting this x1 y1 in the equation 1, so we get this. Simply substitute x1 for x, y1 for y, we end up with this. Okay, this y1 times y1 minus 2a of x1 plus x1, this whole thing gets simplified to y1 square minus 4a x1. Okay, and this y1 y2 minus 2a of x1 plus x2. Here also we have same thing, y1 y2 minus 2a of x1 plus x2. Okay, so these two get cancelled, and anyway we know that s11 is 0, that is y1 square minus 4a x1 is 0, so this is going to be 0. So here we have left hand side 0, right hand side 0, so the equation 1 satisfies the point x1 y1. Similarly, substituting the point x2 y2 in 1, so we get this. Okay, here y2 y1 minus 2a of x2 plus x1. Okay, this is same as the right hand side, these two get cancelled, and here y2 times y2 minus 2a of x2 plus x2. Here we simply substituting x2 for x, y2 for y. Okay, in 1. Fine. So this gets simplified to y2 square minus 4a x2. which is nothing but S22, which is 0, that we know. Okay, so we have left hand side 0, right hand side 0. Again, this equation satisfies the point x2, y2. So therefore, this S1 plus S2 equal to S12 is the line passing through the point x1, y1 and x2, y2. So this line can be represented in terms of S like this: S1 plus S2 equal to S12. Here, this theorem is not about finding the chord equation joining the 2 points x1, y1 and x2, y2 on the parabola. Rather, it is about expressing this chord equation in terms of the parabola s equal to 0. Here we are saying that this chord equation is S1 plus S2 equal to S12. We managed to express this chord equation in terms of the parabola s equal to 0. Fine. Next theorem, the equation of the tangent at P x1 y1 to the parabola s equal to 0 is s1 equal to 0. We are going to prove this theorem for standard equation of the parabola, which is y square minus 4ax equal to 0. But theorem is true for general equation of the parabola. Here s equal to 0 could be representing any general equation of the parabola. Okay, fine. Proof. Here P x1 y1 is the point on the parabola s equal to 0. So we should have s11 equal to 0. Here x1 y1 is the point on the parabola y square minus 4ax equal to 0. So we should have y1 square minus 4a x1 equal to 0. That's what s11, right? Okay. Let us take another point q x2 y2 on the parabola s equal to 0. Okay. Now the tangent at P can be seen as limit of the secant PQ as q tends to P. Okay. Here the tangent at P can be seen as limit of the secant PQ as q tends to P. From the above theorem, the secant equation PQ is S1 plus S2 equal to S12. Right? Okay. So the tangent at P is what? Limit of S1 plus S2 equal to S12 as Q tends to P. Now let us take the limit inside. So we have limit Q tends to P S1 plus limit Q tends to P S2 equal to limit Q tends to P S12. Okay, let us try to understand each limit here. First of all, what is S1? S1 is y1 plus 2a times x plus x1. Okay, if you let q tends to p, that means limit x2 y2 tends to x1 y1. Okay, what happened to this expression? See, this expression is independent of x2 y2, so nothing happened, it will be as it is. Okay, so the limit of s1 as q tends to p will be as it is s1. So this limit going to be equal to s1. Fine. Next, what is s2? S2 is y2 plus 2a times x plus x2. Okay. Now, if you let q tends to p, that is limit x2 y2 tends to x1 y1. What happened to right side expression? So y2 tends to y1, x2 tends to x1. So it will be y1 plus 2a times x plus x1, which is actually s1. Okay, so the limit q tends to p s2 going to be equal to s1. Fine. Next, what is s12? S12 is y1 y2 plus 2a times x1 plus x2. Now, if you let q tends to p, so limit x2 y2 tends to x1 y1. Okay, so what happened to right side expression here? Here x2 tends to x1, y2 tends to y1. So y1 y1 2a times x1 plus x1. So what is this? y1 times y1, y1 square. So this is going to be 4a x1. Okay, which is exactly equal to s11. Okay, So the limit q tends to p s12 going to be s11. So we have this s1 plus s1 equal to s11, but s11 equal to 0. So right hand side we have a 0. So we have this 2s1 equal to 0. That implies s1 equal to 0. So the tangent at p equal to s1 equal to 0. Therefore, the equation of the tangent at a point x1 y1 to the parabola s equal to 0 is s1 equal to 0. Next theorem, the equation of the normal at a point x1 y1 on the parabola s equal to 0 is y minus y1 equal to minus y1 by 2a times x minus x1. Here s equal to 0 denote the standard equation of the parabola. Okay, first let me draw the standard equation of the parabola y square minus 4ax equal to 0. Let me take a point x1 y1 on the parabola. So the tangent is going to be the line touching the parabola at this point. Then the normal equation going to be the line which is perpendicular to the tangent and passing through x1 y1. Okay, so this is the tangent at x1 y1. This is normal. Okay, fine. From the above theorem, we know that the equation of the tangent to the parabola s equal to 0 at x1 y1 is s1 equal to 0. For the standard equation of the parabola y square minus 4ax equal to 0, s1 equal to 0 will be y1 minus 2a of x plus x1 equal to 0. Let me rewrite this s1 equal to 0 like this. Minus 2ax plus y1y minus 2a x1 equal to 0. Okay, so slope of this tangent will be what? Minus coefficient of x by coefficient of y, that is minus of minus 2a by y1, that will be 2a by y1. So therefore the slope of the tangent at x1 y1 is 2a by y1. So the slope of the normal at x1 y1 going to be minus 1 by slope of the tangent, so which is going to be minus y1 by 2a. Okay, so this is the slope of the normal. Now we can write down equation of the normal at x1 y1 as line passing through point x1 y1 and having the slope minus y1 by 2a. So the equation of the line passing through x1 y1 and having the slope minus y1 by 2a going to be this: y minus y1 equal to minus y1 by 2a times x minus x1. So this is the normal equation to s equal 0 at x1 y1, whereas is standard equation of the parabola, which is y square minus 4ax equal to 0. Fine. Now we are going to see equations of tangent and normal to the parabola y square minus 4ax equal 0 in parametric form. Okay, here is the theorem with the two statements. Statement 1, equation of tangent to the parabola y square equal to 4ax at a point t is x minus yt plus at square equal to 0. Statement 2, equation of normal to the parabola y square equal to 4ax at a point t is y plus xt equal to 2at plus atq. At a point t means at a point at square comma 2at. We know that any point on the parabola y square minus 4ax equal 0 will be in this form at square comma 2at for some t belongs to R, right? That's why at a t means we should understand at a point at square comma 2at. Okay, fine. We are simply going to write down this tangent and normal equation, treating that this point is our x1 y1. Okay, we know how to write down tangent and normal equation at a point x1 y1, right? Let's do that. Okay, now equation of a tangent to y square minus 4ax equal to 0 at point x1 y1 is what? y1 minus 2a times x plus x1 equal to 0. Okay, but here our x1 y1 is what? 80 square comma 280. Okay, let us substitute x1 equal to 80 square, y1 equal to 280 here. Okay, what you get? Y times 280 minus 2a times x plus 80 square equal to 0. Okay, now you get 2a yt minus 2a times x plus 80 square equal to 0. If you take 2a common, then you have yt minus x minus 80 square equal to 0. So we must have yt minus x minus 80 square equal to 0 since a is non-zero. Okay. Now the same equation we can also write like this: x minus yt plus 80 square. Okay, simply we are taking minus common. So this is the equation of tangent to y square minus 4ax equal 0 at point T. Okay, fine. Now let us write down equation of the normal at a point T. Okay, first of all, equation of the normal to y square minus 4ax equal 0 at x1 y1 is y minus y1 equal to minus y1 by 2a times x minus x1. Okay, so our point x1 y1 is what? 80 square comma 280. Okay, simply let us substitute 80 square for x1, 280 for y1. So we have y minus 280 equal to minus 280 by 2a times x minus 80 square. Okay, this 2a cancel. Now we have y minus 280 equal to minus tx plus 80 cube. Okay, now we can rewrite this equation as y plus xt equal to 280 plus 80 cube. Okay, so this is the equation of the normal to y square minus 4ax equal 0 at t. T means at a point 80 square comma 280. Okay, fine. Now I am going to list out equations of tangent and normal at a point T for all standard form equations of the parabola. Okay, the first equation that we take is y square equal to 4ax. Okay, at a point T means at a point 80 square comma 280, because the parametric form for this parabola y square equal to 4ax is 80 square comma 280. So at a point 80 square comma 280, the tangent is going to be ty equal to x plus 80 square, and normal is going to be y plus tx equal to 2at plus at cube. We have just seen this from above theorem. Similarly, if you work with the other standard equation of the parabola, which is y square equal to minus 4ax, at a point t, means here the point is minus 80 square comma 280, because the parametric form for this parabola y square equal to minus 4ax is minus 80 square comma 280. So at a point minus 80 square comma 280, the tangent will be ty equal to minus x plus 80 square, and normal will be y minus tx equal to 280 plus 80 cube. If you work with a parabola x square equal to 4ay, and at a point t, means here at a point 280 comma 80 square, as 280 comma 80 square is a parametric form for this parabola x square equal to 4ay. So the tangent at 280 comma 80 square going to be tx equal to y plus 80 square, and normal is going to be x plus ty equal to 280 plus 80 cube. Okay. Here at a point t, means at a point 280 comma minus 80 square, as 280 comma minus 80 square is a parametric form for this parabola x square equal to minus 4ay. So the tangent at a point 280 comma minus 80 square going to be tx equal to minus y plus 80 square, and normal is going to be x minus ty equal to 280 plus 80 cube. Okay. Okay, here is the problem. How many normals can be drawn to the parabola through a given point? We have already looked at the number of tangents that can be drawn to the parabola through an exterior point of the parabola. Now let us look at the same problem for general point. Okay. Let x1, y1 is any point in the plane. So let us consider the parabola y square equal to 4ax. We know that any tangent to this parabola will be in this form, y equal to mx plus a by m. Okay, here m is non-zero. If this tangent passes through given point x1, y1, then we should have y1 equal to mx1 plus a by m. That should give you a quadratic equation, that is x1 m square minus y1m plus a equal to 0, okay, whose discriminant going to be y1 square minus 4a x1, that is s11. Okay, if the given point x1, y1 exterior to the parabola, then the discriminant will be positive, because delta equal to what? S11, and this will be positive if the point is exterior to the parabola. In this case, you will have two real and distinct roots for this quadratic equation. Let me call it star. Okay. So when x1, y1 is exterior to the parabola, then we will have two tangents through x1, y1. One is y equal to m1x plus a by m1. Other one will be y equal to m2x plus a by m2, where m1, m2 are two distinct real roots of the star in this case. Okay. Next case. Case 2. If x1, y1 is the point on the parabola, then the discriminant will be 0, because if x1, y1 is the point on the parabola, then we will have s11 0. So in this case, we will have a real and equal root. We will have only one real root. So in this case, we will have only one tangent through x1, y1, for which the point of contact will be the given point x1, y1 itself. Okay. Next, case 3. If the point x1, y1 is interior to the parabola, in that case, the discriminant will be s11, that is negative. So here, no real roots for m. So in this case, we have no tangents through given point x1, y1. Okay, fine. Now let us try to answer the number of normals that can be drawn to the parabola through a given point. Okay. The equation of the normal in parametric form at 80 square comma 280 for the parabola y square equal to 4ax is y plus xt equal to 280 plus 80 cube. Okay, here let me draw the standard parabola y square equal to 4ax. If you take a point 80 square comma 280 on the parabola, then tangent at this point looks something like this, then normal at this point will be like this. Okay, whose equation going to be y plus xt equal to 280 plus 80 cube. Okay, fine. If this normal passes through given point, say x1 y1, let us say this is a x1 y1 given point, then we should have y1 plus x1t equal to 280 plus 80 cube. Okay, that should give you 80 cube plus 2a minus x1 times t minus y1 equal to 0. So we have this equation in t, which is a cubic equation in t, so it can have at most 3 real roots. Okay, for each real root t of this cubic equation, y plus xt equal to 280 plus 80 cube will be a normal to the parabola y square equal to 4ax through given point x1 y1. Okay, therefore the number of normals to y square equal to 4ax from the point x1 y1 will be equal to the number of distinct real roots of this cubic equation. This cubic equation can have at most 3 distinct real roots. Also, it will have at least one real root because this is an odd degree polynomial equation. So, it will have at least one real root. So, the number of distinct real roots of this cubic equation 1 going to be 1 or 2 or 3. Okay, either 1 or 2 or 3. Okay. We are going to state the criterion for number of normals to the parabola through a given point in terms of criterion for the number of distinct real roots of a cubic equation. Fine? Okay. Here is the criterion for number of normals. Case 1, the first case, special case, if the point x1, y1 is 2a comma 0, let us say if this is axis a comma 0, then 2a comma 0 could be somewhere here. In this case, the normal is that axis itself, which is the normal at vertex 0 0, at which tangent going to be y-axis. Okay. So in this case, the number of normals through the point x1 y1 equal to 1. Okay, fine. Case 2, if x1 y1 is different from 2a comma 0, then we are going to state the criterion in terms of the criterion for number of distinct real roots for this cubic equation. Fine. Okay. We are going to compute something called delta in terms of the coefficient of a cubic equation like this. Here we write delta equal to g square plus 4h square, where g equal to minus y1 by a and h equal to 2a minus x1 by 3a. Here 2a minus x1 is coefficient of t and a is coefficient of t cube. Okay, and minus y1 is constant. So here h is coefficient of t by 3 times coefficient of t cube and g equal to constant by coefficient of t cube. Fine. Then we compute delta as a g square plus 4h square. Okay. Now there is a criterion for number of distinct real roots of this cubic equation in terms of the sign of this delta. Okay. First, if delta positive, then the number of normals through x1 y1 equal to 1. Because if delta positive, then the number of distinct real roots for this cubic equation 1 going to be 1. That's why in this case the number of normals to the parabola through x1, y1 equal to 1. If delta equal to 0, then the number of normals through x1, y1 will be 2. Because if delta equal to 0, the number of distinct real roots for this cubic equation 1 will be equal to 2. That's why in this case, the number of normals through x1, y1 equal to 2. If delta negative, then the number of normals through x1, y1 equal to 3. Because if delta negative, then the number of distinct real roots of this cubic equation will be 3. That's why in this case, the number of normals through x1, y1 will be 3. Okay. This is how you can decide number of normals to the parabola through a given point. Unlike in the tangents case, we have at least one normal to the parabola through a given point. But in the case of tangents, if the point comes from interior of the parabola, then we do not have any tangents. In that case, the number of tangents to the point interior to the parabola is 0. Okay, but that is not the case with our normals. We have at least one normal to the parabola through any point. Okay, fine. Now we are going to see equation of the normal to the parabola in slope form. The equation of the normal to the parabola y square equal to 4ax having the slope m is y equal to mx minus 2am minus am cube. Okay, proof. We know that the equation of the normal to the parabola y square minus 4ax equal 0 at 80 square comma 280 in parametric form is y plus tx equal to 280 plus 80 cube. Let me call it 1. Okay. What should be the slope of this line? Slope of this normal should be minus coefficient of x by coefficient of y. That is minus t by 1. That's going to be minus t. Therefore, slope of the normal at a point 80 square comma 280 m equal to minus t. Okay, that implies t should be equal to minus m. So this is how parameter t connected to slope of the normal. So we get an equation of the normal in slope form simply substituting t equal to minus m in this equation. Okay, in 1. So what do you get here? If you substitute t equal to minus m, y plus, I'm replacing t with a minus m in 1. So y plus minus m of x equal to 2a of minus m plus a of minus m whole square. This is going to be y minus mx equal to minus 2am plus am square. By taking minus mx to the right side, I can rewrite this equation like this. Y equal to mx minus 2am minus am cube. Okay, this is the equation of the normal to the parabola in slope form. Here m is the slope of the normal. Here m denote what? Slope of the normal. Okay. Okay. Now this look like y equal to mx plus c, where c equal to minus 2am minus am cube. Okay, fine. So I can make a note here. The line y equal to mx plus c is normal to the parabola y square equal to 4ax if and only if that c equal to minus 2am minus am cube. Okay, fine. Now let us solve some problems. Okay, problem 1. Find the condition for the straight line Lx plus my plus n equal to 0 to be a tangent to the parabola y square equal to 4ax and find the coordinates of the point of contact. Okay, here let us say this is the parabola y square equal to 4ax, and let me draw the tangent Lx plus my plus n equal to 0. lx plus my plus n equal to 0. Okay. Let us say this is a tangent at some point on the parabola at square comma 2at. Okay. So here solution. So let me call y square equal to 4ax. Let me call it 1. Lx plus my plus n equal to 0. 2. Let's say 2 is tangent to 1 at point 80 square comma 280. But actually tangent to 1 at 80 square comma 280 should be what? X minus yt plus 80 square equal to 0, which is in parametric form, right? Okay, let us call it 3. So in terms of 80 square comma 280, this line should be x minus yt plus 80 square equal to 0. Okay, fine. Now 2 and 3 should be representing same line. Should be representing same line. So the corresponding coefficient must be in same proportion. So we should have L by 1 equal to m by minus t equal to n by at square. Okay. So now from this I get L by 1 equal to m by minus t, that implies t equal to minus m by L. Okay, and from this I will be getting m by minus t equal to n by at square. Okay, that implies t will be equal to minus n by am. Okay, so fine. From these two I can write minus m by l equal to minus n by am. That implies am square equal to nl. Okay, so this is the condition for the line lx plus my plus n equal 0 to be a tangent to the parabola y square equal to 4ax. Okay, fine. Now let us find out the point of contact. Point of contact is what actually in terms of t 80 square comma 280. But we have two choices for t here. You can use anything. So let me take t equal to minus m by l. Then the point 80 square comma 280 going to be a minus m by l whole square 2a minus m by l. So it's going to be a m square by l square comma minus 2am by l. Okay, so this is the point of contact. Okay, fine. Next, problem 2. Show that the straight line 7x plus 6y minus 13 equal to 0 is a tangent to the parabola y square minus 7x minus 8y plus 14 equal to 0 and find the point of contact. Okay, here the slope of the line m is going to be minus 7 by 6, which is not 0. So this is not a horizontal line. So if I can show that the point of intersections with this line and this parabola is only one point, then we can say that this straight line is tangent to this parabola. Also, that point of intersection will be a point of contact. Okay, so let us try to solve for point of intersections. Solution. First, 7x plus 6y minus 13 equal 0. Let's call it 1. And y square minus 7x minus 8y plus 14 equal 0. Let's call it 2. Now let us solve 1 and 2 for point of intersections. Solve 1 and 2 for point of intersections. Okay. First, let us try to eliminate x from 1 and 2. So from 1, I can write x equal to minus 6y plus 13 by 7. Okay. So now we put this value in 2. What you get? Y square minus 7 minus 6y plus 13 by 7 minus 8y plus 14 equal to 0. As you can see, this 7 cancel. Now we have y square plus 6y minus 13 minus 8y plus 14 equal to 0. That implies y square minus 2y plus 1 equal to 0. That implies y minus 1 whole square equal to 0. So we got real and equal roots for y 1 comma 1. Now if we substitute this y equal to 1 in 1, what you get? 7x plus 6 times 1 minus 13 equal to 0. So 7x minus 7 equal to 0. That implies x equal to 1. So x equal to 1, y equal to 1. So therefore, the point of intersection is only one point, that is 1 comma 1. Therefore, hence the straight line 7x plus 6y minus 13 equal to 0 is tangent to this parabola y square minus 7x minus 8y plus 14 equal to 0. And the point of contact going to be this intersection point only. Okay, fine. See, one thing we have to keep in mind here. First of all, this parabola equation we can write like x equal to ay square plus by plus c. That is x equal to some quadratic function of y. So this is the parabola whose axis parallel to x-axis. Now, okay, if you take any horizontal line which is going to meet this parabola at single point, but still this horizontal line is not tangent. Okay, that's why first we have to make sure that this line is not horizontal line. Okay, we looked at a slope which is non-zero, so this line is not horizontal line. Okay, fine. Next problem, problem 3. Prove that the normal chord at the point other than the origin whose ordinate is equal to abscissa subtends a right angle at the focus. Okay, let me draw standard parabola whose equation is y square equal to 4ax. Let's call it 1. Here x is going to be x-axis and whose focus will be S, a comma 0. Let us say P is a point on the parabola whose ordinate is equal to abscissa. Okay, so at this point, if you look at the normal line, first let me draw this tangent. The normal is going to be the line perpendicular to this tangent at this P. Okay, this is the normal line. Okay, then this is going to be normal chord. Okay, so this intersection point we can say Q. So this PQ going to be normal chord. Okay, what we have to show here? We have to show that this normal chord PQ subtends right angle at this focus. That means we have to show this angle is 90 degrees. Fine. First, let us get hold of the coordinates of these end points of the normal chord PQ. Okay, fine. Let me write this P in parametric form. 80 square 280. Since P is the point whose ordinate is equal to abscissa, we should have 80 square equal to 280. That implies T times 80 minus 2a equal to 0. That implies either T equal to 0 or T equal to 2 since a is positive. Okay. Here T equal to 0 will give you origin, but we are talking about the point other than origin, so we have to discard this T equal to 0. We have to go ahead with T equal to 2. Okay, now for T equal to 2, so what is the point? If you substitute T equal to 2, you get a 4a, 4a. So we got these coordinates. P going to be 4a comma 4a. Okay, fine. We got a coordinates for one end point of this normal chord PQ. Okay, we can write this normal equation in parametric form. Y plus xt equal to 2at plus at cube. Here for t equal to 2, this normal equation will be y plus 2x equal to 4a plus 8a, it's going to be 12a. Okay, therefore normal equation at p is going to be what? Y plus 2x equal to 12a. Let's call it 2. Okay, now we want to get hold of coordinates of other endpoints of this normal chord PQ. Okay, fine. So we can see that this Q has intersection point of this normal line and this parabola. Okay, so we can solve this 1 and 2, get the coordinates of Q. Okay, now let us solve 1 and 2 for points of intersections. Points of intersections. Okay, from 2 we have y equal to 12a minus 2x. We put it in 1. What we have here? 12a minus 2x whole square equal to 4ax. Okay. Okay. If I take 2 out from inside, I will get a 4 out. Then 6a minus x whole square equal to 4ax. So we can have now 36a square plus x square minus 12ax equal to ax. Okay. Now x square minus 13ax plus 36a square equal to 0. Now I can write this one, x square minus 9ax minus 4ax plus 36a square equal to 0. So if I take x common, then x minus 9a and 4a common, then x minus 9a. So x minus 4a times x minus 9a equal to 0. So that should give you x equal to 4a, x equal to 9a. For x equal to 4a, the point you get is this p. Okay, we already got it. Now let us focus on this x equal to 9a case. Okay, if you take x equal to 9a, if you put it in 2, what you get? Y plus 2 times 9a equal to 12a. Okay, so that should give you y equal to 12a minus 18a, that will be 6a. Therefore, this q coordinate is going to be 9a comma minus 6a. Okay, therefore q is what? 9a comma minus 6a. Okay, fine. Now if you look at the slope of SP, what is the slope of SP? 4a minus 0 by 4a minus a, that is going to be 4 by 3. What about slope of SQ? Slope of SQ going to be minus 6a minus 0 by 9a minus a, which is going to be minus 6a by 8a, that would be minus 3 by 4. As you can see, slope of SP times slope of SQ is what? 4 by 3 times minus 3 by 4, that equal to minus 1. Therefore, we can say that this normal chord PQ subtends right angle at the focus. Okay, fine. Next problem, problem 4. From an external point P, tangents are drawn to the parabola y square equal to 4ax, and these tangents makes an angle theta 1 theta 2 with its axis such that tan theta 1 plus tan theta 2 is constant b. Then show that P lies on the line y equal to bx. Okay. Let Px1 y1 be external point of this parabola y square equal to 4ax. Let's call it 1. So since P is an external point of this parabola, we must have S11 positive. What is S11? y1 square minus 4ax1 must be positive. Okay, here let me draw a standard parabola whose equation is y square equal to 4ax. This is going to be the axis, which is x-axis only. Okay, let us say external point P location is here, Px1 y1. Okay, so we know that two tangents can be drawn from here. Okay, this is the one, another one could be something like this. Okay, these are the two tangents. Let me say this is L1 equal to 0. Let's say this is L2 equal to 0. Then L1 makes an angle theta 1 with the axis of the parabola, that is x-axis, and L2 makes an angle theta 2 with the axis of the parabola, that is again x-axis. Then the slope of the L1 will be what? slope m1 will be equal to what? By definition it should be tan theta 1, and slope of L2 m2 should be what? By definition that should be tan theta 2. Okay, fine. What is given here? It is given that tan theta 1 plus tan theta 2 is constant B. We know that tangent equation to 1 will be in the form y equal to mx plus a by m. Okay, well, let's call it 2. Okay, so here this 2 passes through external point P x1 y1. Okay, that means we should have y1 equal to mx1 plus a by m. That should give you x1 m square minus y1 m plus a equal to 0. Okay, so this is the quadratic equation in m. Okay, as you can see, this equation 3 is quadratic equation in m. Okay, here x1 y1 a are constant that are known. Okay, so if you think like this is a, this y1 is like a b, then this one like a c, then this look like am square plus bm plus c, which is a quadratic equation in m. Okay, fine. Now the discriminant of this quadratic equation going to be what? B square means y1 square minus 4 x1a. So this is going to be S11, which is positive, as x1 y1 is external point. So 3 will have two real and distinct roots, say m1 m2. Okay, so then what will be the sum of the roots? m1 plus m2 going to be what? Minus b by a, right? So here that means minus of minus y1 by what is a here? X1. Okay, so this is going to be m1 plus m2 equal to, we got y1 by x1. Okay, but what is m1 plus m2? What is m1? m1 is tan theta 1 and m2 is tan theta 2. That equal to, we got y1 by x1. But tan theta 1 plus tan theta 2 is constant b, right? So we have b equal to y1 by x1, that implies y1 equal to bx1. Okay, so therefore we can say that this x1 y1 lies on the line y equal to bx. Okay, fine. Next problem 5. Show that common tangent to the parabola y square equal to 4ax and x square equal to 4b by is x a to the power of 1 by 3 plus yb to the power of 1 by 3 plus a to the power of 2 by 3 times b to the power of 2 by 3 equal to 0. Here we are given two parabolas, y square equal to 4ax, let me call it 1, x square equal to 4by, let me call it 2. Okay, first of all, we know that any tangent equation to the parabola y square equal to 4ax will be in the form y equal to mx plus a by m for m not equal to 0. Okay, we know that any tangent equation to the parabola 1 will be in the form y equal to mx plus a by m for m not equal to 0. Okay. Now let us say for a particular value of m equal to m naught, the line y equal to m naught x plus a by m naught is also tangent to the parabola 2. Now let us say for m equal to m naught, particular value of m naught, the line y equal to m naught x plus a by m naught, let me call it 4, is also tangent to parabola 2. The way equation 4 looks, it's pretty clear that the 4 is tangent to parabola 1, but we have chosen m naught so that this y equal to m naught x plus a by m naught is also tangent to parabola 2. Okay. If the line 4 is tangent to the parabola 2, then there should be only one point of intersection between this parabola 2 and line 4. Okay. There should be only one point of intersection for the line 4 and the parabola 2, since 4 is also tangent to parabola 2, right? So when we solve for points of intersection for 2 and 4, we should be getting only one point as a point of intersection. Fine? Okay. Now solve 2 and 4. Okay. So simply take y equal to m naught x plus a by m naught and plugging in 2. So what you get? X square equal to 4b m naught x plus a by m naught. Okay. So this gets simplified to m naught x square equal to 4b m naught square x plus 4ba equal to 0. That should give you m naught x square minus 4b m naught square x minus 4ba equal to 0. Let's call it 5. Then this 5 must have a real and equal root. Okay. Then this 5 must have real and equal roots, so that we get only one point of intersection. That happens only when discriminant of this 5 is 0. If you compare this equation 5 with a quadratic equation ax square plus bx plus c, this m naught is going to be a, here minus 4b m naught square going to be b, and minus 4b going to be c. Okay. So what should be the discriminant? It's going to be minus 4b m naught square whole square minus 4 m naught minus 4ba equal to 0. This discriminant must be 0. So that will give me 16b square m naught to the power of 4 plus 16 m naught ab equal to 0. Now if I take 16b m naught common, then I will have b m naught cube plus a equal to 0. That implies b m naught cube plus a must be 0, since b m naught is non-zero. Okay, so that implies m naught must be equal to minus a to the power of 1 by 3 by b to the power of 1 by 3. Okay, now we plug in m naught in 4. Okay, now put this m naught equal to minus a to the power of 1 by 3 by b to the power of 1 by 3 in equation 4. That is a common tangent, right? So what we get here, y equal to minus a to the power of 1 by 3 by b to the power of 1 by 3 x plus a by minus a to the power of 1 by 3 by b to the power of 1 by 3. Okay, in the next step we can write y equal to minus a to the power of 1 by 3 x by b to the power of 1 by 3 minus a to the power of 2 by 3 times b to the power of 1 by 3. Okay, now in the next step, if you cross multiply, if you cross multiply, then you will end up with b to the power of 1 by 3 y equal to minus a to the power of 1 by 3 x minus a to the power of 2 by 3 times b to the power of 2 by 3. Okay, now if you bring right hand side things to left hand side, then you will end up with this equation, which is a common tangent to these two parabolas. Y square equal to 4ax, x square equal to 4by. Fine. Okay, let me stop now. Thank you.